Welcome to my channel. In this video, we are going to discuss about a process, program versus process states, process state transition diagram, process control block. The process can be thought of as a program in execution. A process will need certain resources. Counts the resources such as CPU time, memory, files, input-output devices to accomplish the task. A process is basically a unit of work in most of the computer system. Operating system processes execute system code. Similarly, I can say a user processes execute the user code. All these processes may execute concurrently. There are a lot of responsibilities of the operating system concerned to the process. The scheduling of the processes. Many processes may be active. Scheduling of those processes should be done by the OS. The provision of mechanism for synchronization. When more than one process is active in the system, there is a need of synchronization. A lot of concepts, what all we discuss in the OS, are applicable to our day-to-day life. I love this particular subject, teaching, because a lot of concepts, what we discuss in the operating system, are applicable to day-to-day life. Even asynchronization is very important, not only between the processes, even between the human beings. A provision of communication. There is a need of communication between the processes. These are all subheading, a subtopic which can be discussed later. The provision of a deadlock handling for the processes, very interesting chapter, a deadlock handling, and this is another responsibility of the operating system related to the process. If you want to know what is a process, simply if you press Ctrl Alt Delete in your computer, you'll find a lot of processes running in your computer, even though you have not yet started any program, anything else. A lot of programs or a process will be available when you press a Ctrl Alt Delete. We'll not go in deep like this, considering your laptop, etc. We'll restrict our discussion to the textbook and the syllabus. In some books they use as a job, in some books they use as a process. Both are same. Whenever it is a used job, you take it as a process only. And process includes usually a program counter, a stack, a data section. And there is a difference between the process and a program. Program is basically a passive entity. For example, a file stored in your pen drive, maybe hard disk somewhere. Process is active entity where it is having a program counter. All of you know a program counter specify the address of the next instruction to be executed. As process executes, it changes its state. For example, these are the states. Take one by one. New. A process is being created. We say it is a new process is created. Running. When instructions are being executed, I can say the process is in running state. Sometimes it may need some IO or event to occur. It may be waiting. And ready means the process is waiting for the CPU, or I can say a processor. Don't get confused with the process and the processor. Processor is nothing but a CPU. Terminated, the process has finished a complete execution. Any program which is residing in the secondary memory, or in fact any file you want to edit, you want to do anything, first you should double click on that so that it will be brought from the main memory to the secondary memory to the main memory. For example, a program, a code is there in the secondary memory. When you click it, double click it, it will be brought from secondary memory to the main memory. And there it will be kept in the queue. Like that, few programs you might have brought from the secondary memory to the main memory, all are kept in the ready queue. Among these, some programs which are in the ready queue, any one will be selected and it will move from ready to the run state. Means you are allocating a CPU to that particular one process which moves its state from ready to the running state. And once if it executes completely, it will be terminated. When it's terminated, all the resources, you might have given the memory, you might have given the CPU, you might have given the IO device, all will be deallocated, will be taken back from that process. Or sometimes the program has not yet executed, that process has not yet completed, but it needs some IO. For example, you are reading something from the keyboard, then you want to continue. So that time, the process will change its state from run to wait. So till the user enters some numbers, so it will be in the waiting state. Say for example, you are reading something from the keyboard, you have entered the number now. It will not go to the run state, it will go to the wait state to ready state. When IO is completion or any event is, you are waiting for the event to occur, so it will move from wait state to ready state. Or another chance is, sometimes if it is running, time is over. You are allocating a particular time for each and every process. If time is over, it will be moved back to the ready. Or for example, interrupt occurs or higher priority process comes in the ready state. Now you are leaving the present process. So that time it will move from run to ready whenever the interrupt occurs. Just whatever we have discussed just now. Remember, this is selection is done by a long-term scheduler. Many are there in the secondary. From secondary, will bring few to the main memory. This work is done by a long-term scheduler. And in this ready queue, if I have a few processes, any one will be selected so that a CPU can be allocated. That work is done by the short-term scheduler. You have a lot of scheduling algorithms. Remember all those what we discussed in this chapter are a short-term scheduler. Why it is called a short-term? Continuously this will run. Frequency of this short-term scheduler will be more compared to the long-term scheduler. Whenever a complete process is over, terminated, then only the new process will be brought from the secondary memory to the main memory. So it will be executed late. So long-term scheduler frequency is less, its frequency is more. So just revise it whatever I have told just now. New, okay, admitted, ready, and selected, running, over, terminated. If IO needed, it will go to the waiting state. IO is over, ready state. If any interrupt occurs, run to ready. And remember this long-term scheduler and short-term scheduler. Most of you might have heard Jataka. Many says the Jataka of a person will be having all the information related to that person. Similarly, I can say a Jataka of a process will be there in the process control block. It is having all the information related to that particular process. Each process is represented in the operating system by a process control block. In short, we say PCB. It contains many pieces of information. Process state, whether the process is ready, run, waiting, etc. Program counter, where the next instruction is available. A CPU registers, program counter, stack pointer, instruction register, CPU scheduling information, memory management information. When we discuss a separate chapter on this memory management information, you will come to know what are the information can be kept in the process control block. Well, if the base and limit registers, the page tables, etc., I can say, and accounting information and amount of CPUs used, IO status information, all these will be available in the process control block. And remember, each and every process will be having a one process control block. There all the information will be available. In assembly programming, most of you may be remembering the number of push operation should be equal to the number of pop operation in the subroutine. Why? Because the return address is stored in the stack whenever you go for use a call instruction. When you go to the subroutine, by default return address will be stored in the stack, and if you use a number of push equal to number of pop, then return address will not be disturbed. How the CPU switches from one program to the other program? Try to understand, it is very simple. See, beginning it is executing a P0, how it will switch over to the P1, again how it will come back to the P0. So observe carefully. Now P0 is executing and say interrupt occurs, then what I will do? I will save the state of a process P0 in the PCB0, and now I have to switch over to the P1. What I will do? I will take information from the PCB1 to the CPU, then I will start executing a P1. Again, I will save the state of a P1 to PCB1. Again, I will reload a state from the PCB0, so I can start a P0 execution. So this is a way how CPU switches from P0 to P1, again back from P1 to P0. You can pause the video or you can revise, go through once again, try to understand. Summary, what all we have discussed. The process states: new, ready, running, wait and terminated. Process state diagram, just try to revise this, and process control block we have discussed. This is a reference what I have used. For more information you can visit my following channel, blogs and YouTube channel. Thank you for watching this video.